All right, here we go. Maybe
If it doesn't work, we're going to move on anyway, because this shouldn't take this much time. All right, we ready to go? So really, this isn't that hard. I hope that you didn't think it was that hard. One equation, right? Delta E equals what? Q plus W. All right. So we just had to plug these things in and make sure that we understood them correctly. So we have a system absorbs 85 kilojoules. So is that a plus or a minus sign? That's a plus sign. Of heat from its surroundings while doing 29 kilojoules of work on the surroundings. So is that a minus or a plus? That's a minus. Okay? If it absorbs, it's endo. If it does work, it's exo. So we have 85, and you don't have to put the plus, but I'm going to for emphasis. Kilojoules, I would write the unit because sometimes they mess up the units, just like in part B. And you add negative 29 kilojoules to that. And really you're just subtracting, so you end up with 56 kilojoules, right? Who had that one right? Raise your hand. Okay. Let's, not that bad, right? Part B, same idea. This one's nice. Let's see, delta E equals Q plus W. And it just gave you the signs. What was the trick here? All right. I'm going to convert this one. If you convert it the other way, it won't matter. So I'm going to convert this. So I have 1.5 minus, plus minus 6, or 0.657. I end up with 8, what? 8.4? All right, 0.84, and this would be what unit that I used? Kilojoules. If you got 840 joules, that's the same answer. We okay with that? Who had that one right? Raise your hands. Okay. 843 is fine too. All right, C. The system releases, that's a key word, 57.5. If it releases, what sign? Negative of heat while doing 13.5 kilojoules of work. If I'm doing work, what sign? Negative. Doing work's always a negative. All right, so we have delta E equals negative 57.5 minus, plus minus, right? 13.5. So really I'm just subtracting and I end up with negative 71 kilojoules. I did that last hour too. 71 kilojoules. Who had that answer? Good. Who had all three of them? Good. Who's grateful that, man, that wasn't very hard. I can do algebra all day long. Okay, well good. Let's see if you really can. Next up. 33A. Both of these are just kind of thinkers. We'll work through them together. 33 says the complete combustion of acetic acid to form that at constant pressure releases that many kilojoules of heat per mole. Write a balanced thermochemical equation for this reaction. All right, so first off, let's write out the reaction. It's the combustion of acetic acid. So it is HC2H3O2. It's the combustion, so it's reacting with who? Oxygen produces H2O and CO2. All right. See if you can balance it. Don't spend too long. Okay, who has it balanced? Raise your hands. All right. What did you guys get? 1, 2, 2, 2. Who agrees? Raise your hands.
4, 2, 4, 4, 4.
1, 2, 4, 4, 4.
No, 2, 4, 4, 4.
Which is the same thing.
Yeah, pretty much.
Right? Okay, so that's the balanced chemical equation. Are you okay with that? Now, this problem says write a balanced thermochemical equation for this reaction. All right, so it's just a teeny bit tricky. Well, I shouldn't even say tricky, different. All right, it tells you that this releases this many kilojoules of heat per mole of this. You all right with that? So you can write this in two ways. You can put at the end that delta H equals, it released it, right? I already forgot there, 8 something. Anyone remember what it was? 8717. Okay? That is one way to completely correctly answer this question. You just throw on that delta H is equal to that. Or you can put plus right here, 871.7 kilojoules. Why did I put it on the right side? Because it's released, or it's produced, or it's a product. How come I didn't put plus negative?
Because that side release.
All right. It would be redundant, and you would actually end up with a double negative, and you'd actually be wrong. Okay? By it being on the right side, that is telling us that it is released. That negative sign is telling us it is being released. Who's with me? Raise your hands if you're with me right now. Okay. So, conceptually, you all right with that? A thermodynamic equation simply means that you throw on the enthalpy change either as a product or reactant, or you just write delta H. Most reactions will be written with it just at the end as this. All right, part C I would like you to read. Well, I'll read it. It says, consider the following reaction which occurs at room temperature and pressure. 2Cl gas goes to Cl2 gas. Our change in enthalpy is negative 243.4 kilojoules. Which has the higher enthalpy under these conditions? 2Cl or Cl2. I want you to talk with your lab partner, discuss that question, and come up with your best answer. Okay, about 20, 30 more seconds tops.
Do it.
All right, let's do it. So if I call this A and this B, so let's vote. Who thinks A has higher enthalpy under these conditions? Raise your hands. Okay, then who thinks B?
No, they have the same.
They have the same. Sorry, who thinks they have the same? All right, that's not an option. So that was wrong.
Okay.
The correct answer is A.
Oh, wow.
What does this negative sign mean?
Really long energy.
It means that as this process happened, energy is lost. All right? In fact, negative 243.4 kilojoules were lost. So if I lost energy to go to B, that means A had more energy in the first place.
Yeah.
All right, now I don't remember how far we got yesterday, but did we talk about how the change in enthalpy is equal to the enthalpy of products minus the enthalpy of reactants?
That was the last thing we did. You just it's not equal.
Okay. So, well, here you go. This is a fairly simple concept. The overall change in our enthalpy will be equal to how much enthalpy our products or our final state has minus how much enthalpy our initial or our reactants have. You okay with that? So if I know the enthalpy that I start with and the enthalpy that I end with, I could calculate the change. Right? That's not hard. All right, well, let's think this through with this problem. In order for this answer to be a negative value, what does that mean about these two things in relationship to each other?
Reactions higher than
What's that?
the reactions are higher than
All right, it means that my reactants have more energy. Or enthalpy is fine, same thing. Okay, than my products. It means the second number has to be bigger. All right, well, if it was positive then, what would have to happen? The first number would have to be bigger, correct? All right, so that helps answer this as well. We end up with a negative value because our reactants had higher enthalpy than our products. Okay. Here we go. This is where it gets fun. 5.39. Now, these are taken from the white book, but they're the same problems as the black book, just a different number. So we're just working through your homework together right now. Take a few minutes. I will tell you that in the long run, this problem's really simple. But when you first look at it, I have no doubt that it might not look like it's simple. And then for ease of this problem, I want you to ignore this M. The question's really asking you per millimole, but we'll just say per mole for right now. Raise your hands right now if you have no idea what to do. Okay. Anyone think they do know what to do?
Probably just doing it wrong.
Yeah, you can practice.
What?
If I'm doing something, we're probably doing it wrong.
I guess, I'm reading things.
But
Yeah, that's one thing. That's right. Is that like this? Yeah.
These steps up the challenge a little bit higher.
I mean, only have two numbers.
You're going to divide, multiply, subtract, right? Square root. Take the derivative of it. All right. Let me help you with part A. I'm going to pull these pieces right here up. Whoa. You know, if I can, I'm always going to pull the picket fence up, right? So, think about things. When you have a balanced chemical equation and I give you numbers, you're most likely going to have to do stoichiometry, which means we're probably going to have to use a picket fence. You all right with that? So I look at part A. I only gave you one number. So what do you do with the thing I give you? What do you always do with the number I give you in a picket fence? You start with it. So I gave you 0.200 mole of AgCl. Now, the only other thing I gave you was the balanced equation. Please look. We'll try this green. This number right here, I'm not liking it. We're going to go bright yellow because yellow's beautiful. This number right here is the amount of kilojoules released per 1 mole of that, 1 mole of that, or 1 mole of that. So that is a proportion per 1 mole. You okay with that concept? This value is per mole. It always is. And it's always per 1 mole. So let's come down here. What do I need to get rid of? Moles. So for every 1 mole, what's the only thing the problem gave me? I had negative 65.5 kilojoules. That leaves me with the unit of kilojoules. Is that the unit I want? It absolutely is. So I take 1/5 of this, and it was 13.1 kilojoules. Yep, sorry, thank you. It is negative 13.1 kilojoules. Okay. Now, see if you can do number or letter B. It's different but super similar. There's just one problem. I'm going to get rid of this, and I'm going to put a black line right here, and see if you can figure it out from there. You already know you're doing it wrong? You got the last one right without any help? Do I believe in you more than you believe in you?
I said already know. At least you're not calling rules.
Oh, I thought you said you did not know what you were going to do.
Reborn data seems good.
Oh, you're screwed.
That escalated super fast.
So mad right now.
143 is a number that you might be looking for. And it's probably some decimal, but 143 is good enough. And remember, we're ignoring the millimole. I'll explain the millimole here in a second, but we can just do it without it. If you've moved to part C. Oops.
For C, can we just say that it's not applicable because it doesn't solve?
No,
We can't?
we cannot say that
I know.
because it's telling you that it does.
Lies.
But I'm proud of you for thinking about last chapter.
You want to say changes in chapter 5?
Well, apparently dropping my mouse tries to close the program. All right. Do we have an answer? Is it like 2 point something or 1 point something? I can't remember. Negative what? Negative 1.14. I'm just gonna go there because I'm out of room. There we go. All right, so let's Jeopardy this thing. That's the answer, but what's the problem? So start how if I give you a number, you got to start there. 2.50 grams of AgCl. Do I want grams in my answer? No, so I have to calculate the grams of AgCl, and that was 143 point something, but I just said use 143. And anytime we find the molar mass, it's per what? 1 mole of the same thing. Do I want mole in my answer? No, but I have a relationship right here that says for every this amount of kilojoules, I have that many moles. So 1 mole for every negative 65.5 kilojoules. Do the math, get this answer, and feel good that you can do hard things. Who had negative 1.1 something? Raise your hands. Okay, Paula, that was most of you. Part C. Part C seems really uncomfortable, right, Stephen?
Okay.
How come?
Because it says that it's precipitate.
All right, because it says silver chloride, which you all know by now is a precipitate, dissociates. In the 80s, we would say, homie, don't play that. Yeah. Oh, we don't play that. Ask your parents. They have to be around 38 to 42. All right. But guess what? I don't care. We're still going to do it, and then we're going to explain. So here's the deal. Did we ever get to a slide that I said it was the truth about enthalpy?
Oh, that big sheet.
It's forever away from now, but we can get there. Whoa.
Oh, I think you passed it.
I did. Right there. I drew this, right? 2 logs was twice as much as 1 log, didn't I? All right. Then, this is the one we need for part C. It says that delta H for reaction in the forward direction is equal in size but opposite in sign for delta H in the reverse reaction.
Got it.
Are we okay with that? All right. So, for example, water is in a river and it's just flowing and it goes over a waterfall. All right. It went over this waterfall. In order for me to pump the water back up, I have to put in the exact same amount of energy it gave off when it fell down, right?
Yep.
You with me on that?
Yes, sir.
An equation or reaction is the same way. Naturally, an equation will go from one way to the other. It will go the direction that's thermodynamically favored or downhill. But I can force it to go the other way, but if I force it, I have to provide the energy or the work. Are you okay with that?
Yes, sir.
So the reverse is always the opposite sign. Now we're going to need this one later. It says that the enthalpy for a reaction depends on the state of the products and the state of the reactants. Just remember that. Now let me go 100 miles this way. Oh, too far. Whoa, right here, right? Okay, so this one's not very hard. Calculate delta H when this mole of silver dissociates in water. That is the reverse reaction, right? So it's the same process math-wise. I just switch a sign. 0.150 mole. And now I have 65.5 kilojoules per every 1 mole. And I just multiply them, and what do I get? 9.83 kJs, right? So look, what is this really telling me? We got to make sure we understand what this is saying.
You need a sheet. How much energy we need to put in.
All right. Okay, it says it's endothermic, but it's also saying I have to supply this much energy in order to make this dissolve. But look, we know this didn't dissolve. We put stuff together and it became a solid, right?
Yeah.
Well, this is why. Because nature always wants to be where there's lower enthalpy. Which side here has lower enthalpy? The negative means this has lower enthalpy. So silver chloride is a precipitate because it is what we call thermodynamically favored. All right? Nature, just like you, we don't like to necessarily be super energetic and always like busy and all that. It seeks laziness, so to say, or lower enthalpies. So which one's favored? Silver chloride. Now let's just do some quick math. And you don't have to do this, but just follow my logic here. 9.83 times 1,000 will tell me the joules here, right? So it's 9,830 joules for me to get this to break apart. Might not seem like a very big number, but take this number and multiply it by 4.184. Someone do that for me fast. If I remember, it's 41,003. Is this right? All right. So this is 41,003 calories of energy I have to put in to get this to dissolve. That might not sound like a number that really means much to you, but it means that I could heat 41,003 grams of H2O 1 degree Celsius. That's a lot of energy, isn't it? All right? So it takes a lot of energy or a lot of work or whatever, yada, 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 to do this.
basically if you heat that up, you can make it dissolve.
Yeah, if I put in a lot of energy or work, I can break them apart. I can reverse nature.
Is it going to dissolve or dissociate? It have to dissociate, right, to be a reverse reaction.
It's dissociate is the correct term. Did you have a question, Penfold?
The same
Okay,
question.
sorry.
Boiling
Yes.
water with that in it.
True. Dissolving just means one AgCl, this falls apart from another AgCl, like sugar dissolves. Dissociates is the correct way to say it. All right. So we can see based on math,
One mole, what would you do if you had like different molar ratios in the equation, like that combustion reaction we just did?
whoa, my goodness, what a great question. That is exactly what this question is addressing. Does this reaction look uncomfortable to anybody? What? It's got the F word in it right there. We hate fractions in science, don't we?
So times the whole equation.
Okay, well, all that we would do is multiply it all by 2, right?
Yeah.
So it would be, let's go yellow. I like the yellow. That was good
How
contrast.
is that even possible to have?
I'll tell you. So this would really be 2. I'm going to write them down here. And it's not 6, it's 3.
All right.
2. I made that mistake last hour myself, so you're in good company if you said 6. It's 2, 3, 2, 3, right?
4.
Yeah, sorry, 4. I wrote 4. Are you okay with that? Okay, but why is it this way then? All right, thank you. It's because, let's go, what color would stand out super bright? This will. Right there will. Here we go. Write this in your notes somewhere. Enthalpies. I don't know if I spelled that right. I don't care. Are always listed per 1 mole of whatever we're talking about. Okay? It's generally first reactant listed. Okay, like 99% we can get away with that. Okay, so this is a truth about this class. Enthalpies are always listed per 1 mole of whatever we define it, but usually the first reactant listed. That didn't quite stand out as much as I thought it would, did it? Okay, now I'm going to get rid of all this here in a second, so make sure and write that down. So one of the questions, B, asks us to write it out balanced normally. So 2, 3, 2, 4, that's the answer to B. Letter A is easy. What is the enthalpy change of the reverse reaction? You would just go like this and put a plus sign, right? You okay with that?
Yeah.
All right. But part C, I'm going to get rid of this. Still in part B. What is delta H for the reaction represented by how it was previously written? With the 2, 3, 2, 4. What is this value if you write it that way? All right, good. Negative 1, 4, 5, 3. Is that right?
Yeah.
But is this the right value? It's not the value you would use in any calculations. You would use this because that is listed per mole. All right, so look. You must get comfortable with these because you will see them from now on. The fraction is there so that this is a 1. And the fraction is only there if you have an odd number.
So the first enthalpy number is the one that we use for calculations, but in reality, the actual enthalpy number is that bottom number.
Yep, pretty much. And now, Christine, you were uncomfortable right here with this 3/2. You said, is that even possible? Yes, it is. It's not saying I have 3/2 of an O2 atom. It's saying I have 1.5 moles of O2, which is extremely possible. Yeah, remember these things are the moles, not like the actual atoms themselves or molecules in that instance. All right, it's okay. So remember for sure, if it's a fraction, it means, or well, it's there because it's trying to give you this value per 1. All right, part C. Which is more likely to be thermodynamically favored? All right, I used this term a second ago. What does thermodynamically favored mean? It means which side has lower enthalpy. So looking up here, which side has lower enthalpy? What does the negative sign mean? It lost energy, so this side has lower enthalpy. Now, we already went over this earlier, except we were defining it as the one which had more, so it's kind of annoying. But write this down. Hopefully I didn't delete this slide. Oh, poop. Yes. Okay. So the first thing, and I'm sure I spelled 20 of the words wrong, but I don't care. The thing with the star is what thermodynamically even means. And then the next two are your nuggets. So thermodynamically favored means which side has lower enthalpy. Because nature favors lower energy. All right, so then the first, I'll put a star so you don't, well, I don't know. This is not a negative sign, it was just a dash. How about an arrow? All right, so if delta H is negative, then products have lower enthalpy and are the thermodynamically favored side. And then the reverse sentence is just the opposite. If delta H is positive, then the reactants have lower enthalpy and TDF. TDF means thermodynamically favored. All right. That was a lot of stuff, but it's all pretty important. Now, the last one, this one really requires some serious thinking. If the reaction were written to produce water as a gas instead of water as a liquid, would you expect the magnitude of delta H to increase, decrease, or stay the same? And then it asks you to explain. I want you to really think about that one, because it is a thinker, and see if you can come up with the answer. Okay? So as written, it had liquid, but we're going to switch that out for a gas, and it's wondering how that will affect this value. Who has no idea? Oh, who knows the answer then? Okay. Are we almost out of here? I better hurry then. The answer is that it becomes less negative. So, or the technical answers say it increases, but it would be like instead of negative 726, it would be like negative 500. Because instead of releasing all the same energy, some of that energy is stuck in the gaseous liquid itself. It has enthalpy in and of itself, so less of it is just straight released as heat. Who understood that little thing I just said right there?
I think I misunderstood the question.
Okay, mathematically, right here, if delta H is equal to the sum of your products minus the sum of your reactants, the enthalpy of gaseous water is higher, so you have a bigger number, but you're subtracting the same number from it, so your answer is less negative or more towards the positive. It's a tricky question, especially because you're dealing with negative numbers. So some people think increases would mean negative 900, but it's not.